Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on September 18, 2025, which is just yesterday. The standout result is that stronger regularization, smart epoching, and ensembling beat conventional data-constrained recipes, reaching an estimated best asymptotic loss around 3.17 and delivering about 5.17 times better data efficiency at 200 million tokens than the baseline. The paper is titled Pretraining under Infinite Compute, and the implications for model training are quite significant. In short, the study argues that in a compute-rich, data-poor world, tuning weight decay, scaling parameters, using ensembles, and distilling them yields durable gains. On X, researchers emphasize data as the bottleneck, advocate heavy regularization, asymptote-based scaling, and ensembles for 5 times data efficiency, with one post drawing strong engagement at about 200 likes. Alright, the previous segment highlighted stronger regularization and ensembles as the winning recipe. Figure 1 now compares scaling strategies at a fixed 200 million tokens and shows validation loss versus total parameter count. The red, standard recipe plateaus, which signals overfitting despite more compute. The purple regularized curve keeps dropping and fits a power law, so its asymptote sits near 3.43. The teal ensembling curve falls further, and the dotted lines mark data efficiency gains up to about 5.17 times for the joint strategy. Okay, the previous figure emphasized asymptotic gains from regularization and ensembles. Figure 2 shows what happens when only the standard knobs are used at 200 million tokens. The left panel plots loss versus epoch count for 300 million parameters, which initially drops but then rises sharply, showing overfitting because repeated passes start memorizing the small dataset. The right panel varies parameter count with tuned epochs, and the loss barely improves and even worsens at 1.4 billion, so bigger models do not rescue fixed data. So, the previous figure showed that naively scaling parameters stalls. Figure 3 presents regularized parameter scaling and contrasts two recipes at 200 million tokens. The red epoch recipe flattens and even ticks up, which indicates overfitting despite larger models. The purple regularized recipe keeps decreasing roughly like 0.05 over n to the 1.02 plus 3.43, so the curve trends toward an asymptote near 3.43. This monotone drop means stronger weight decay, with tuned epochs and learning rate lets bigger models actually help. Alright, the previous figure showed a smooth power law drop for regularized single models. Figure 4 contrasts that with ensemble member scaling and plots loss versus total parameter count. The teal ensemble curve falls faster and heads to a lower asymptote around 3.34, which beats the purple single model curve that trends toward 3.43. This means training several 300 million models and averaging their logits can outperform one larger model with the same total parameters, because independent members capture complementary features. So, the previous figure stressed that ensembles beat single models at fixed tokens. Table 1 reports continued pre-training on Llama 3 billion with only 4 billion tokens, and shows accuracy gains from lower batch size, epoching, and K-member ensembling. The averages rise from about 24 to 35 with the single epoch model, and then to roughly 41 with K equals 8, which even exceeds the 73 billion token baseline at about 39. These numbers imply a 17.5 times data efficiency lift because 8 epoch models on 4 billion tokens surpass training on 73 billion. Wrapping up, 2 takeaways stand out. Strong regularization with tuned epoching keeps loss decreasing under fixed data, and ensembles, then distillation, convert extra compute into real data efficiency, reaching roughly 5 times better use of tokens. The broader implication is clear. In a compute-rich future, smarter recipes beat bigger single models. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.